Drawing Lewis structures. Atoms in covalently bonded molecules will have 8 valence electrons. And this is called the octet rule. And there are very many exceptions, but we should always try to satisfy the octet rule. These atoms will have shared and unshared pairs of electrons. So the electrons get paired up. Always try to put them in groups of 2. Here we have our carbon dioxide molecule, which I have shared with you before, but you see that each oxygen molecule has 8 valence electrons, and it does this through sharing with the carbon. And my carbon also has 8, and you can count them there: 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8. So this is what's called a Lewis structure, where you take the dot diagrams, or the Lewis dot diagrams, sometimes they're called, and you put it together kind of like a puzzle. And you can slide the electrons around a little bit, and you see that this is what's happened with carbon. The dots slid around so that they're in between the oxygen atoms on either side, and you see that oxygen did too. So we have this oxygen right here, and we can see that the electrons slid over, and our carbon, drawn like this, we have these ones slide over also. And this is a double bond. So what's happening when I put these Lewis dot diagrams together, these atoms together? So these are some rules that you should know. First of all, the electrons determine the shape of the molecule. Electrons, because they're negative, they repel each other, and they want to stay as far away from each other as possible. And you really need to think 3D. Now this electron repulsion, it's also called VSEPR theory, valence shell electron pair repulsion theory. And it means that our molecules will be 3D, so they're not going to be flat on a plane. They will be 3D structures. In the classroom, we will work with the ball and stick models to make these 3D structures. These shared electron pairs, they form a bond in between molecules. If you have 2 dots, then that is a single bond. If you have 4 dots or 4 electrons, that would be a double bond. And so instead of drawing those 4 dots, you can draw 2 lines. The AP board is very, very flexible when you're drawing these, and if you do draw the dots out, they usually accept that. But it's just easier to draw the lines. So 1 line for every 2 dots. Triple bond would be 6 electrons. So here we have some molecules. So here's CO2. We see that this one is a linear shape, and we do have bonded pairs and unbonded pairs. So these are our bonded pairs, and that's because they're between 2 atoms. And then here's our unbonded pairs. And we're always going to pair them up. So draw them as 2 dots, not like as 4 dots scattered, because they are paired up. Here we have water over here. How we put this one together is we draw water's Lewis dot diagram, which looks like this, okay? And then I can draw hydrogen's dot diagram. And then all I do is I just stick it together. So I'm going to put the H here. Maybe I'll draw X's for the hydrogen. And I have another H here, X's. So notice it makes this bent shape, not a linear shape. And that's because of these unbonded electron pairs. Unbonded electron pairs will push the bonded pairs closer together. So instead of having oxygen and the hydrogens out like this, which you might suppose, that's not what happens. Because oxygen has these bonded pairs and then my electrons right there, you're going to see that the hydrogens will hook on right where those dots are. I always like to start with my dot diagrams and see how I can put them together. There are rules for drawing Lewis structures. These are found at the beginning of the packet, so you should not have to take notes on this. It's already done for you, the first or second page of your packet. But here's your rules. So count the valence electrons. So when you draw these dot diagrams, every valence electron needs to be present and accounted for. You can draw the skeletal structure to connect them with bonds. The central atom is usually written first in the formula, or is present in the smallest amount. So if there's only one of something, it might be the central atom. You should never, ever, ever put hydrogen as the central atom. It's too small. It can only bond once. Also, other elements that should never go in the center are your halogens. These are called terminal atoms. So hydrogen's a terminal atom, halogen's a terminal atom, oxygen sometimes is. So just watch out for that. Each single bond uses 2 valence electrons, and then if you have extra electrons, you distribute them to make octets. You should have memorized that carbon always has 4 bonds. So it will have 4 bonds and there will be no unshared dot pairs. And then, as I said, this is probably the third time, hydrogen can only form 1 bond. If there are too few electrons to form octets, that's when you're going to form double or triple bonds. Again, always try to form an octet. Except for these guys. So the exceptions to the octet rule. Hydrogen only needs 2 dots. It's just too small. It can't handle 8. Beryllium is also very small. It needs a quartet or only 4 electrons around it or 2 bonds. Boron and aluminum need a sextet or 3 bonds or 6 electrons. Watch out for odd electrons. Try not to have an odd leftover electron. You should always pair them up. And then we are going to learn in AP Chemistry expanded octets. So this is not taught in my honors chemistry class or in regular general chemistry, but we will learn it in AP Chemistry. So I'm going to go through with you how to draw these Lewis structures. We will discuss the shape, and we will also memorize the bond angles for each of the shapes. And again, for all of these, you must have the valence electrons. So I'm going to start with the valence electrons, but then I'm going to pretty much use the dot diagrams to help me connect everything together. So beryllium has 2 valence electrons, and each of the chlorines have 7. So the total number of valence electrons or electrons in the structure, I have to have 16. So if I look at beryllium, beryllium has these 2 dots here. So that would be its dot diagram. When you are putting these Lewis structures together, you're going to move the dots around a little bit. And so instead of having them next to each other, I'm going to put them far away from each other, okay? And then chlorine is going to look the same. So chlorine, it has 7 valence electrons. I'm going to end up putting my chlorine here. And then it looks like that. This double electron here, that's going to be my bond. So I'm just going to draw a line for those two. And then on this one, I'm going to do the same thing. So I'm going to have my 7 electrons. I'm going to make a bond right there. And there's my beryllium chloride. I can double check to make sure I have 16. So remember, every line counts for 2. So I can count 2, 4, 6, 8, 10, 12, 14, 16 valence electrons on this. Okay. Don't write the numbers there. I'm just trying to teach you digitally, so it's hard to point on this. But this shape is linear. The bonded pairs will repel each other, and they'll get as far away from each other as possible. And so the bond angle, it will be 180 degrees. Okay, so linear and our bond angle of 180 degrees. And this is what our alkali metals do, alkaline earths. So our alkaline earth metal family makes these linear shapes. Notice for your rules, beryllium just needs that quartet or 4 electrons because it's so small, and we do have that there. I'm just going to get rid of this extra chlorine that I did right there. Okay, so we can just see it a little bit better. Okay, let's come to this next one. So we have boron. The boron family has 3 valence electrons. Fluorine is a halogen. They have 7. They always have 7 dots around them. They're always terminal, so on the end. So drawing my dot diagram, boron, I would draw it like this. Okay. Now these dots are going to spread out when we're bonding. So I'm just going to move the dots around a little bit. And then I'm going to draw on my fluorine. So fluorine is just like that chlorine we just did. So we have a total of 7 dots around it. So I'm just going to tack on each of the fluorines. And I'm going to form a bond right there because that represents 2. 1, 2, 3, 4, 5, 6. And then here that represents my bond. And one more. 1, 2, 3, 4, 5, 6. And instead of having that dot there, I'm going to just make a bond. Just double check that we have all the electrons. So each fluorine has 8 now. So 8 plus 8 plus 8. I do have a total of 24, which was my 21 plus my 3. That does give me 24. So I accounted for every valence electron. Let me just erase this fluorine right here. And what shape is this? This is called trigonal planar. When we look at the bond angles here, if you take a circle, which is 360 degrees, and divide it by 3, you're going to get 120. So that's my bond angle here. The family that does this is the boron family. And again, it's because the boron family has 3 valence electrons. All right, let's go do our next shape. So we have carbon, and we should know that carbon has 4 bonds. It has 4 valence electrons. Each of those electrons is going to form a bond with something else. Here's another halogen. This time I have 4 of them. So 28. 28 plus 4, I should have 32 valence electrons. Let's start off with carbon. So carbon, draw the 4 dots. It looks like this. Okay. Remember, we pair them up, but when you're drawing these Lewis structures, you can slide things around. I'm just going to slide one of those dots around to this other side. And then I'm going to draw in my chlorines. Each chlorine has 7. And then I'm going to make a bond here. And then chlorine, make a bond here. Finish out the dots. Chlorine here and a chlorine here. You might think that this is flat and that there's 90 degrees on either side, but we need to think 3D. Those bonded pairs, they are going to repel each other, and we're actually going to get a shape that is called tetrahedral. And the bond angles are not 90 degrees, 90 degrees, and 180 degrees. They are 109.5 degrees away from each other. Everything in the carbon family does this shape, and that is because it has those 4 valence electrons. So, and you do need to memorize the bond angles. That for sure will be on your AP test. So it looks drawn flat like this, but it spreads out. So sometimes you see it drawn like this, and then draw the little dots around it. Anytime you have a halogen, it will always have 3 sets of unbonded pairs. So it looks like that. Let's make sure that we have all our valence electrons. So each chlorine has 8. So we have 8 plus 8 plus 8 plus 8. We do get the 32. And our chlorine also has 8 because it has those 4 bonds. So it has 2, 4, 6, 8. So our octet is satisfied with this carbon tetrachloride. I'm just going to free up some space here on this slide. So let me just erase this. And let's come here to our next molecule here. So this is ammonia, NH3. Nitrogen has 5 valence electrons. Hydrogens, they each have 1. So I should have 8 valence electrons for this. And I'm going to start off with nitrogen. The dot diagram, 1, 2, 3, 4, 5. And then I can see where the hydrogens go in. So I'm going to put a hydrogen. Remember, a hydrogen just has 1 dot. So I'm going to put a hydrogen right here. And I'm going to make a bond out of a dot from hydrogen and a dot from nitrogen. And then I'm going to put one here and make a bond, and right here and make a bond. Okay, so around my central molecule, I have 3 bonded pairs. And this is again around the central atom, I should say, not molecule. The central atom has 3 bonded pairs, and it has 1 unbonded pair. And as far as now this unbonded pair is going to do something. It's going to spread way out, and you wouldn't draw that line, but those electrons are going to spread way out, and they're going to push these bonds closer to each other than the tetrahedral. So where your tetrahedral has a bond angle of 109.5, this has a bond angle of 107. So they're pushed just a little bit closer together. And again, it's because of that unbonded pair. Now, what's the family that makes this? This would be the nitrogen family. So anything in the nitrogen family as the central atom, it's going to make this shape, which I didn't name. The shape is trigonal pyramidal because it looks like a little pyramid. And let's go, and I think I'm going to clear my slides so I have a little bit more room. Okay, so we're on water. So let's count valence electrons. So each hydrogen has 1 for a total of 2, and oxygen has 6. So I should have 8 valence electrons. So I'm going to start with the oxygen as the central atom because hydrogen's never in the middle. I'm going to draw my dot diagram for oxygen. It looks like this. And then I'm going to add my hydrogens. So hydrogen just have 1 dot. So I'm going to make a bond right there and I'm going to make a bond right here. This one has 2 unbonded pairs, and this one has 2 unbonded pairs. As far as where the electrons are, this is a modified tetrahedral. So this one is a trigonal pyramidal. It is also a modified tetrahedral. The shape of this one is called bent. I do have all my valence electrons, 2, 4, 6, 8. You can count around that oxygen, and each hydrogen has 2. The bond angles for this, because I have 2 unbonded pairs, and you wouldn't draw these lines, but I'm just trying to demonstrate that these unbonded electrons, they spread way out. They're going to push these bonds closer together, and so they're going to be even closer than that NH3. So these are going to have a bond angle of 104.5 degrees. What makes a bent shape? Well, the oxygen family. So the oxygen family will make molecules that have 2 unbonded pairs, and that's what's going to cause the bonds to be closer together that gives us this bent shape. All right, let's do the next one. So this is PCl5. I'm going to just do it up here. Phosphorus is in the nitrogen family, so it's going to look like this. And then I need to put 5 chlorines around there. Wow, where am I going to put those 5 chlorines? Okay, so I can see how I put them here. So I get those, and I have a chlorine here. So I get that one, and then I get this one, and I still have 2 more chlorines to draw. So what I'm going to do is I'm just going to spread these dots around just a little bit further apart, and I'm going to put my chlorines there. Boy, what is this thing? So phosphorus is a larger atom, and because it's larger, it can make what's called an expanded octet. And that's what's happening here. Because how many valence electrons are around that phosphorus? Well, 2, 4, 6, 8, 10. Wow. And that's because phosphorus is a larger atom than, say, nitrogen. So the nitrogen, so phosphorus can make that trigonal pyramidal shape, but it can also make these what's called an expanded octet. We do need to double check and make sure we have the proper number of valence electrons, but I drew them from the dot structure, so we should have everything there. But phosphorus has 5 valence electrons. Each chlorine has 7. 7 times 5 would be 35, so I should have 40 valence electrons in that structure, and I do. Each chlorine has 8, so 8 times 5, I get the 40 valence electrons, okay? Let's look at the shape. So this shape, I end up having 3 go around in a ring. So these ones are on a plane, okay? And so on these, they're all at a distance of 120 degrees away from each other. And then this chlorine at the top, I think I'm just going to move it over just a little bit. We will see it go up and down with the other one on the bottom. So we have between here and here, we have 180 degrees. So this is a shape called trigonal bipyramidal. And there are lots of different central atoms that can do this. So you might get phosphorus like this, but you also might get a larger halogen that can do this. All right, so that's, again, an expanded octet. We have one more to do, and I don't really have a lot of room, so I'm going to erase this all again. And let's look at the SF6. So that's my last one here. So if I look at sulfur, it's the first one listed, so I'm going to assume that's my central atom. Besides, fluorines can't ever be central atoms. They're a halogen. So sulfur has 6 valence electrons, and each fluorine has 7. 7 times 6, 42. So I should have 48 electrons in this structure. So let's figure out where they're all going to go, okay? So I figure I can put 1 here and 1 here. So that's 1, 2. And then I can split 2 of these dots, 3, 4, and then it looks 5, 6. So I'm just going to spread things out so I can see that I am going to have 6 bonds around this sulfur. So let me just draw it so it looks a little bit less ski-wampus, because those dots are going to spread out and each of them will be attached to a fluorine. So I'm going to have 4 fluorines come around here, and then 2 go up and down. And then anytime you have a halogen, you have to draw the 3 unbonded pairs. So yes, this has a lot of dots. All right, so these are on a plane and they have a distance of 90 degrees from each other. From this bond to this bond is 90 degrees all the way around. And then we have a distance of 180 between the top and the bottom. And the distance between the plane and this bond is also 90 degrees. So this one is called an octahedral. So, and again, it's an expanded octet. So, because sulfur has 2, 4, 6, 8, 10, 12 electrons around it. And sulfur can handle this because it's a larger atom. It's in the 3rd energy level. So all of its s and p electrons get involved in the bonding to make this octahedral. So when you look at the degrees, these guys all have 90 degrees bond angles. So this slide shows and sums up what I was drawing before. There are electron domain families, and I'll talk about that when we get to the tetrahedral shape. But let's look at our linear shape. So a linear, this has 180 degrees. And then let's look at what happens if you have 3 electron domains around a central atom. So we have the typical trigonal planar, which is this one, with 120 degrees. And this is a shape I didn't talk about, but there are 3 electron domains or 3 areas around the central atom where you will find either bonded pairs or unbonded pairs. And this one has 1 unbonded pair and 2 unbonded pairs. I don't see this one too often in chemistry, so that's why I didn't draw it before, but it is considered bent because that unbonded pair pushes the bonded pair closer together. So this one you would predict that it is closer than the 120 degrees. On the AP test, the bond angles, they're in a range. So you don't have to guess just one number. Go ahead and guess one number, but the answer key will have a range that is correct. And then let's look at this. If there are 4 electron domains or 4 areas where electrons are coming off, then you have these shapes. Tetrahedral is when you have, they're all bonded, so 4 bonded pairs and 0 unbonded. Trigonal pyramidal, you have 1 unbonded and 3 bonded pairs. And on this one, you have 2 unbonded and 2 bonded pairs, and with a bent shape. So notice there's 2 bent shapes. And then there's this one, I rounded 107. So again, there's a range. That is a correct answer. The expanded octets, I drew the trigonal bipyramidal. This is when you have 5 bonded pairs. If you have 1 unbonded pair in that series, that is a shape called seesaw. So that one would be 1 unbonded and 4 bonded. That's how that's described, and it looks kind of like a seesaw on either side if the dots are going up. T-shape, this would be 2 unbonded pairs and 3 bonded pairs. And you can see those unbonded pairs again would push the bonded pairs closer together. And they call it T-shape because sometimes it does look like this, with the dots out this way. But those unbonded pairs do push those bonded pairs a little bit closer together. So you can see it's not 90, it's a little bit closer together than 90. And then last but not least, we have linear. So in a plane around here, I have my unbonded pairs. Again, they're as far away from each other as possible. They're 120 degrees away from each other. And then we have my bonded pairs. Those are 180 degrees from each other, but that's a linear. So those are all modifications of having 5 electron domains or 5 areas where those electrons will be. Last but not least, we have our, if we have 6 electron domains, and I drew the octahedral for you. So where there's 6 bonds coming away from a central atom. We have square pyramidal that has 1 unbonded pair and that has 5 bonded pairs. And then this one is called square planar. So this is the only one that it's actually flat. So you have your unbonded pairs coming up and down. But again, that's called square planar, and everything's 90 degrees. Notice that there's 2 linears. This one is the one that has unbonded pairs. So you need to study these shapes. There is a chart at the beginning of your packet that shows all these shapes and shows how many bonded pairs, how many unbonded pairs. And a lot of times you just kind of play around with it, and then you can always Google the shape just to see if you're right. So I mentioned family groups with what shapes you would have. If you have your alkaline earths, if you have your alkali metals, there's just 1 bonded pair. Alkaline earths, they would have 2. And that's where we get a linear shape. If we have, this is the boron family, it would be trigonal planar. This is the carbon family. It would be tetrahedral. When we have the trigonal pyramidal, that's our nitrogen family. Again, trigonal pyramidal, it's a variation of the tetrahedral. We've just taken off 1 bond and put in an unbonded pair. And then we have bent, 2 bonding pairs and 2 non-bonding pairs. That's the oxygen family. Here's a chart that sums up the approximate angle. Again, on the AP test, there will be a range that's correct. So just pick a number and then hope you're within the range. Let's do more practice with Lewis structures. So we want to draw the Lewis structure and list the bond angle and the shape. So let's try this one. This is ammonium ion. So I'm going to start off with nitrogen looking like this. It has 5 valence electrons, and each hydrogen has 1 for a total of 4. And that plus means that we have 1 electron less. So as far as valence electrons, we have 5 plus 4 is 9, but minus 1, we should have 8 valence electrons. So I am going to put on my hydrogen, so I know 1 goes there, and I know 1 goes there, and I know 1 goes there. And then I'm going to take off 1 of the hydrogens, so I'm going to erase it. And then I know 1 goes here. Okay, so this is what my molecule looks like. This is ammonium. I have to put the whole molecule in brackets and say it's positive. Again, that positive means that there's 1 less electron. Okay, so what shape would this be? Well, if it has 4 bonded pairs and no unbonded pairs, this is tetrahedral. And I would guess that my angles right here is going to be 109.5. Let's do this next one. So I have selenium, Sb. I'm going to look that up. That's in the oxygen family. So I'm going to draw the dot diagram. And then, so it has 6 valence electrons. Each bromine has 7. And there's 4 of them for 28. 28 plus 6. I need to have 34 dots, or 34 electrons. All right, where are we going to put the bromine? So I know that 1's going to go there. And I know 1's going to go here. Okay, and then I need to have 2 more. So I am going to take this dot and I'm going to spread it out a little bit. So I'm going to put 1 bromine here and 1 here. Okay, so we have an unbonded pair here, and then there's 4 bonded pairs. So this is when there's 5 electron domains. So 5 electron domains. So this is in the trigonal bipyramidal family, but I've taken off 1 of the bonds, and so this is going to be seesaw shaped. And as far as the bond angles go, I would say that these bonds are put closer together. So between this and this, it wouldn't be 180. It would be, I don't know, 170, I would guess. And then between these guys, I would guess like, I don't know, maybe 100 degrees. Okay. Um, so a little bit closer than like a tetrahedral would be. All right. So again, 5 electron domains, but seesaw shape because there's one of those bonds missing. So on the PowerPoint, there's some charts that you can study these. Here's some more charts, again, talking about VSEPR theory, how, again, the bonds in the electrons, they repel each other, so we have 3D shapes. And then I'm going to let you look at the PowerPoint for this so you can see how unbonded electron pairs push the bonded pairs closer together. And here's some of the more complicated shapes, how that all looks like. Again, this is on the PowerPoint. And we've seen that chart before.